Hello, and welcome to this presentation, Understanding Voltage Controlled Oscillators. In this short presentation, we'll provide a technical overview of voltage controlled oscillators, or VCOs, and in particular, how VCOs are measured or characterized. One important aspect of any type of oscillator characterization is phase noise, and this is true for VCOs as well. We won't be covering phase noise testing in this presentation, but if you're interested in learning more about phase noise and how it's measured, you might also want to watch the presentation Understanding Phase Noise Fundamentals. To understand voltage-controlled oscillators, we'll start with a quick explanation of what an oscillator is. Broadly speaking, an oscillator is an electronic device that produces a repeating signal or waveform. This is usually, but not always, a sinusoidal signal. Oscillators are one of the most fundamental components in a wide variety of electronic devices, and many RF devices have multiple oscillators. The primary characteristic of an oscillator is the frequency of the signal that it generates, but we're also often very concerned with the quality or the purity of the oscillator. For example, how stable are the output frequency and power? Are significant harmonics or spurious signals also present? Since the quality of an oscillator's output can have a significant impact on the function or behavior of the overall system, it's important to measure or characterize oscillators. For some oscillators, the output frequency is a constant or fixed value. That is, the frequency depends on the design of the oscillator, or on the components in a feedback network. In other cases, the output frequency of the oscillator may be variable. The frequency can be dynamically changed based on an external input. A voltage-controlled oscillator is an oscillator whose output frequency is controlled by an external voltage, called the tune or control voltage. In this presentation, we'll refer to this voltage as V-tune. For example, increasing or decreasing V-tune causes the oscillator output frequency to increase or decrease. The tune voltage may be changed in discrete steps, as shown here, or continuously. There are a wide variety of VCOs with different form factors and different specifications or operating parameters. VCOs are also used in a wide variety of applications. One of the most common applications of VCOs is in phase lock loops or synthesizers. They're also often used in communication systems. For example, we can create analog FM modulation by continually varying V-tune. Or we can implement FSK, or frequency hopping, by changing V-tune in discrete steps. Another place where VCOs are helpful is in radar applications, in particular in linear FM or chirped radar and in FMCW. Just as there are many different VCO applications, there are also many different ways of designing VCOs. Some common oscillator designs have names such as Colpitts, Hartley, etc. A key component in most VCO designs is a varactor diode, which acts as a variable capacitance. The choice of which design to use affects the VCO's performance and characteristics, and in most cases, various trade-offs must be made. For example, how wide should we make the VCO's frequency or tuning range? A wideband VCO can be used to cover a wide range of frequencies, and this eliminates the need for multiple narrowband VCOs. This is particularly useful in radar or electronic warfare applications. On the other hand, narrowband VCOs generally have better phase noise and would be more suitable for use in a PLL. Measuring the behavior or characterizing the VCO is therefore an important part of the VCO design and debug process. Aside from basic parameters like frequency range and output power, characterization is often concerned with how much our VCO deviates from ideal behavior. To begin with, the output of an ideal VCO at a given tune or control voltage would have a constant frequency and minimum phase noise. The VCO would be unaffected by minor deviations in the supply voltage or by changes in the impedance into which it's operating. And across its entire operating range, an ideal VCO would have an output power and a current consumption that are independent of frequency. It would also have linear tuning or sensitivity, meaning that every increase in X volts always increases the output frequency by Y hertz. And our ideal VCO would not produce any harmonics or other types of spurious emissions. All of these parameters, or deviations from ideal behavior, are part of VCO characterization. Now that we understand what VCOs are and why characterization is important, let's talk about how VCOs are characterized. There are various methods and instruments that can be used when characterizing VCOs. For any test setup, there are two very important requirements. The first is the ability to supply very stable and highly precise fixed and variable voltages. The second is the ability to very precisely measure changes in the VCO's output frequency, power, phase noise, etc., as one of these voltages is changed. Because VCOs are a special type of oscillator, phase noise testers with integrated voltage sources are often used to characterize VCOs. In most cases, these instruments also provide automatic measurement of common VCO characteristics, such as output frequency versus tune voltage, and this automation both increases accuracy as well as decreases test time. Let's look at an example of a typical VCO test configuration. 3 connections need to be made to our VCO. First, the VCO needs a supply voltage to operate. This is normally a fixed voltage. Next, we connect the tuning or control voltage, V-tune. This is a variable voltage that controls the VCO output frequency. And finally, the VCO RF output is connected to the RF input of our instrument, which then measures and plots the output characteristics of our VCO as a function of the variable input voltage. The most basic VCO measurements are tuning range, frequency pushing, frequency pulling, sensitivity, output power, current or power consumption, and harmonic power. We'll be covering each of these measurements in this presentation. Using a combined phase noise and VCO tester also allows measurements of phase and AM noise as a function of the tune voltage. The integrated spectrum analyzer functionality found in some phase noise testers also makes it possible to measure additional VCO characteristics, such as settling time and spurious emissions. Let's start with tuning range, the most fundamental characteristic of a VCO. Tuning range is the difference between the minimum and maximum VCO output frequencies. We determine this by sweeping the tuning voltage and measuring the output frequency. In this example, we sweep the tune voltage between 0 and 12 volts and plot the output frequency as a function of tuning voltage. The difference between the minimum and maximum output frequencies is the tuning range. Ideally, the plotted line would be straight or have a constant slope, something we'll come back to shortly. Note too that although VCO output frequency is supposed to be purely a function of the tune voltage, there are other factors that can affect output frequency. 2 of the more important ones are frequency pushing and frequency pulling, so let's take a few moments to go over each of these. Frequency pushing is a measure of how much the VCO output frequency changes as the supply voltage changes. We want, and we expect, the VCO output frequency to change when the tune voltage changes, but the output frequency of real-world VCOs often is also a function of the supply voltage. Even very small variations in our supply voltage may cause undesired frequency changes and/or phase noise. Frequency pushing is the reason why it's important to use very stable, low-noise supply voltages with VCOs. And frequency pushing can also occur when the VCO supplies a battery, whose voltage begins to drop over time. We characterize frequency pushing by fixing the tune voltage and then varying the supply voltage over a given range. In our example, we'll fix V-tune at 10.8 volts, which corresponds to a VCO output frequency of 600 MHz. Our VCO has a standard supply voltage of 12 volts, but to test frequency pushing, we'll sweep the supply voltage between 8 and 16 volts and record the output frequency over this voltage range. Here, the VCO output frequency varies from 591 MHz to 602 MHz, and so our frequency pushing is 1.375 MHz per volt. The VCO output frequency can also vary based on the load impedance, and this is called frequency, or sometimes load, pulling. This is important because in many applications, we can't guarantee that the VCO will always see a constant or see a matched load impedance. In order to test frequency pulling, we need a directional coupler and some type of variable impedance load, such as a phase shifter, a sliding short, a line stretcher, etc. A spectrum or phase noise analyzer is then used to measure output frequency at different load impedances. Frequency pulling is expressed in megahertz, peak to peak, and shows the maximum deviation from the nominal output frequency. Since this change is a function of the output impedance, it's necessary to specify the range of impedances, or VISWAR values, over which pulling was measured. Another VCO measurement related to output frequency is tuning sensitivity. This is the change in output frequency per unit change in tuning voltage. In other words, does each additional tune volt change the output frequency by the same amount? Sensitivity is therefore measured in megahertz per volt. Let's go back to our frequency versus tune voltage measurement from earlier. We can use the max and min frequencies to calculate the tuning sensitivity across the tune voltage range. Here, 22.5 megahertz per volt. Ideally, we want the tuning sensitivity to be as constant as possible over the tune voltage range. That is, we want our plot of F out versus V tune to have a constant slope. Having a consistent or flat tuning sensitivity makes it easier to tune the VCO, since a simple linear equation can be used to calculate the necessary tune voltage needed to produce a given output frequency. Now let's look at output power versus tune voltage. VCOs are often connected to other devices, such as mixers, so it's important that the VCO output power be known and be appropriate for the connected device. This situation is somewhat complicated by the fact that VCO output power is often different at different output frequencies. We can characterize this by plotting output power versus the tuning voltage. When making power measurements, the load impedance should be specified, since it affects the amount of delivered power, and in most cases the standard RF impedance of 50 ohms is used. The current versus voltage measurement answers the question, how much supply current does the VCO draw at different tuning voltages? If sensitivity is linear, this measurement also provides current consumption as a function of VCO frequency. Ideally, the current consumption should be as low as possible and flat across the tune voltage range. For a given supply voltage, higher current means higher power, so this measurement is particularly useful when characterizing VCOs used in battery-powered applications, where power consumption is often a significant concern. Like all other types of oscillators, VCOs generate harmonics, which are signals that appear at integer multiples of the fundamental frequency. Harmonics are almost always undesirable, and therefore the level of these harmonics should be kept as low as possible. Tens of dB is a common design goal. Note that some types of VCOs may even incorporate filters or other methods for suppressing harmonics. We measure the power of harmonics as a function of tune voltage, plotting the levels of the fundamental, the second harmonic, and the third harmonic. Although we measure these powers in absolute units, such as dBm, in many cases harmonic power is reported in dBc, that is, power relative to the carrier or fundamental. Let's end with a brief summary. A voltage-controlled oscillator, or VCO, is a device that produces an output signal whose frequency can be changed or controlled by means of an external tuning voltage. VCOs are used in many different applications and are one of the fundamental building blocks of RF systems. There are numerous ways of designing VCOs, and the behavior of a VCO is largely a function of the chosen design. Therefore, it's important to measure or characterize VCOs. Most VCO characterization involves varying or sweeping the tune voltage, although we've also seen how things like the supply voltage or load impedance can affect the VCO output. Because VCOs are a type of oscillator, VCO characterization is often performed using phase noise testers. VCO characterization requires precise voltage sources, which can be adjusted while simultaneously measuring the VCO output. But the ability to make other measurements, such as phase noise, settling time, or spurious emissions, are also useful in characterizing VCOs. This concludes our presentation, Understanding Voltage-Controlled Oscillators. Thanks for watching.